Okay, kiddos. Here's an example of an Atwood machine and a description of how to solve it. So there's a pulley and there's a massless rope or cable that runs over the pulley, and attached to it are two different masses. So if these masses were the same mass, nothing would happen. But because one is greater than the other, the force on this mass due to gravity is more than the force due to this mass, and obviously it's going to accelerate. So this is going to move downward, and this is going to move upward. Because the string, cable, pulley, or because the string or cable or rope doesn't stretch, the acceleration of this downward is the same as the acceleration of this upward. So to understand this better, we think of the two masses that are connected together as the system. Okay, and this system is going to have some force acting on it, and it's going to experience some acceleration. So what we're looking for usually is the acceleration of the masses and then the tension in the rope. So tension is just another word for force, and it's the force that would be in a cable or string or rope. Okay, so given that, let's take a look at what we have here. This question gives us this situation and asks us to find these two quantities. It actually gave us a hint, and that was to use simultaneous equations, which you can if you solve for tension first. That's sort of more challenging, so this is easier if we solve for the acceleration first. So, considering the system to be this, we look at, in using F equals ma, we find the net force, meaning the result of all the forces acting on this. Okay, so the tension we can basically ignore. The rope doesn't stretch. You know, the 5 pulling the 3 this way and the 3 pulling the 5 this way cancel out. The force that actually goes to accelerate this system is we have this weight and we have this weight. And because this weight is more than this weight, it's obviously going to pull downward. But the total force, the sum of all the forces acting on this, is the heavy one minus the light one. So we have 49 newtons downward here and 29.4 newtons downward here. The difference in those is the actual force that goes to accelerate these masses. So take a look at this maybe. So here's a graphic description of that. We have the heavy mass and the light mass. Force downward here, force downward here. And because this is accelerating downward, we have that the downward force is greater than the upward force. And because the small mass accelerates upward, we know that the upward force is greater than the downward force. So that is this right here. Okay. And then the result of all the forces acting on it is the big one minus the small one. So in our calculation over here, we have that the net force, the result of these forces, is equal to the mass that is being accelerated, notice how that is both masses, times the acceleration. And doing some simple math gives us that the acceleration is 2.45 meters per second, which makes sense. It's something between 0 and 9.8, okay? Like, if this were infinitely light, this acceleration would be 9.8, and if they were the exact same mass, the acceleration would be 0. So it's something in between that. Once we have found the acceleration, we can consider or look at each mass separately to find the tension. So for the small one, notice how we're doing tension minus 29.4. We know that this is larger than this, and that is equal to mass, just this mass, times its acceleration, which we know, giving us this for tension. And we do the same thing for the large mass. Notice how it is weight minus tension, because weight is greater than tension, and the acceleration acceleration is 2.45, mass of this is 5, and we get tension equals 36.75 newtons. If you were solving something like this and you ended up with different values, you know you made a mistake somewhere. Okay, so that's a description of how to calculate the acceleration and tension in the rope of an Atwood machine.